Now we're going to start looking at actual geometries of molecules. And again, we need to know two basic facts about any element or any atom to know what its geometry is. How many atoms is it bonded to? And how many lone pairs does it have? So we start with what's known as the parent geometry. This is based solely off the number of electron domains. So we need to know the number of domains, what the geometry is. We can talk about what the bond angles are, and then we'll show a picture of it. So remember, again, that ultimately the goal is always that a molecule sets up in a way so that the electrons are as far apart from each other as possible. So we can start with 2 electron domains, and that means our central atom is going to be bonded to 2 other atoms. The way they can be furthest apart from each other would be in a linear arrangement where the bond angle is 180 degrees. That one's fairly easy to represent in 2 dimensions. And looks like that. Again, we have our central atom here, and our 2 atoms that it's bonded to are 180 degrees apart. All right, we can go to 3 domains. This is known as trigonal planar. Bond angles, 120 degrees. And it looks like this. Again, we've got 1 atom in the middle, and we have the other 3 atoms as far away from each other as possible. So that ends up being 120 degrees. Up to 4 domains. This is known as tetrahedral. Bond angles here are 109.5 degrees. And you can see its representation here. So notice what you have is, again, we have a central atom. And 4 atoms. These 2 are in the same plane as the paper, or as the page. This one is coming out toward you, and this one is pointed away from you. Tetrahedral ends up being very important because that's what we find primarily for carbon. We have 5 electron domains, known as trigonal bipyramidal. And what are the bond angles here? What's the bond angle? Well, for trigonal bipyramidal, it turns out we have 2 different bond angles. First, if you look around the center, here, you can see that looks very much like the trigonal planar. So we have 120 degree bond angles there. But we also have what very clearly looks like a right angle. And so there are also 90 degree bond angles in a trigonal bipyramidal structure. Finally, we can look at 6 electron domains. Now it doesn't stop here. There are 7 electron domain structures. It's just we don't need those in this course. This is known as octahedral with bond angles of 90 degrees. and it has its structure there. All right, so this is what's known as parent geometry or molecular geometry. But we also need to get more specific. And so when we're going to get more specific, we're going to talk about molecular geometry. So this is influenced by both the number of lone pairs as well as the number of bonds. And so maybe the best example to start with is we could look at CH4 versus ammonia versus water. And we can draw all of those out. Now, if drawing out Lewis structures at this point isn't very straightforward, then that's something you're going to want to go back and spend some more time on. But notice the differences here. All three of these molecules have 4 electron domains. In the case of the carbon and methane, it's 4 bonds. For ammonia, it's 3 bonds and 1 lone pair. And for water, it's 2 bonds and 2 lone pairs. Does that mean that each of these molecules have a different molecular geometry? The answer is yes. So let's start with 2 electron domains. Turns out there's only one way to do that, which is 2 bonds and no lone pairs. And we can see that in a molecule like hydrogen cyanide or carbon disulfide. Again, we can see 2 bonds and no lone pairs. And so that will be linear. Bond angle of 180 degrees. All right, now we can go up to 3 electron domains. And this gives us two possibilities. 3 bonds, no lone pairs, or 2 bonds and 1 lone pair. With 3 bonds and no lone pairs, we have trigonal planar. With a bond angle of 120 degrees. 2 bonds and 1 lone pair is referred to as bent. And the bond angle here is a little bit less than 120 degrees. Why less than 120? Well, we've replaced one of the bonds now with a lone pair. And lone pairs, it turns out, are more repulsive than bonds are. They need more space. And so what this lone pair here is going to do is it's actually going to push these other bonds even further away. And that's going to make the bond angles slightly under 120 degrees. All right, what about 4 domains? So at 4 domains, we have 3 possibilities. We can have no lone pairs. We've seen this example already. This is methane. Which is tetrahedral. And 109.5 for the bond angles. So one thing that you may be noticing is that when there's no lone pairs, that means the parent geometry and the molecular geometry are going to be the same. All right, we've already seen our example of the next 2. So 3 bonds, 1 lone pair, and then 2 bonds and 2 lone pairs. 3 bonds, 1 lone pair is ammonia is an example. And over here we have water. The geometries here, for ammonia we have what's known as trigonal pyramidal. And for water, we have bent. But notice, it's not the same bent as we saw for 2 bonds and 1 lone pair. Bond angles for trigonal pyramidal are about 107 degrees. And for water, about 104.5. Again, it's because of the size of the lone pair, it pushes the rest of the bonds together. All right, we can now go to 5 domains. And we're going to have 4 possibilities here. 0 lone pairs, 1 lone pair, 2 lone pairs, and 3 lone pairs. For no lone pairs, we've already seen its geometry because, again, remember that when the number of lone pairs is 0, the parent geometry and the molecular geometry are the same. So as an example here, we might have PF5. That looks like that. As we said, this is known as trigonal bipyramidal. And the bond angles are 90 and 120. Now with this structure, if we're going to add a lone pair, we actually have a difference in the positions. And so the lone pair is going to go to the spot where there's more room. And that's going to be one of these spots where the bonds are further apart. So an example of this molecule, one of these might be something like SF4. So here's our representation in 2 dimensions. And here's another picture of that. bond angles here are going to be slightly decreased again by the addition of the lone pair. So instead of 90 and 120, they end up at 88 and 118. And the name of this geometry, and this is one you might even be able to see if you use your imagination. And unfortunately, this is as good as my art skills get. But if you could imagine, these are two people on a seesaw. And that actually is the name of the geometry, is seesaw. For two lone pairs, we might have a molecule such as chlorine trifluoride. And now two of those positions around the middle will be taken up by lone pairs. This one also has a logical name, and this representation may show it to you even better. So what do we think that looks like? So that is known as T-shaped. And the bond angles are just even a little bit smaller, 86 and 116. Finally, three lone pairs might include a molecule such as xenon difluoride. Now all three sites around the center are occupied by lone pairs. And so as you can see fairly clearly from this drawing, the fluorines are now 180 degrees apart, and this is linear. Finally, we have 6 domains. We can start with SF6, which has no lone pairs, but 6 bonds. This is known as octahedral. Bond angles are all 90 degrees. Now, in the octahedral geometry, when we add a lone pair, all 6 positions are geometrically equivalent. So it doesn't matter where the lone pair goes. So one lone pair. We can see that in bromine pentafluoride. This is known as square pyramidal. Bond angles here, again, slightly condensed because of the lone pair pushing away. So we end up at about 88 degrees. And finally, 2 lone pairs. We can see here is known as square planar. Bond angles of 90 degrees. The lone pairs are going to be up above and up below. They're staying as far away from each other as possible, and that leaves the rest of the molecule as a square with bond angles of 90 degrees. So that's our final piece of lecture for Chapter 8. At this point, you should work on some practice. The relevant practice exercise here is in class exercise number 11 Vsepr. And you'll see in that exercise I've given you 11 molecules, and it's basically go through the steps of coming up with the Lewis structure. And in that, I want you to ignore part 5, which talks about hybridization. Also ignore 6 and 7, the number of sigma and pi bonds. That's something we'll talk about much later. But basically what I want in each of these 11 examples is to draw the structure, draw the Lewis structure, and then figure out the parent geometry and the molecular geometry.